Hi everybody, this is the lecture on section 4.5 on the dimension of a vector space. Okay, consider a vector space V and a basis B equal to V1 to VC for V. That is, right, what's basis mean? B is linearly independent and spans V. Okay? For each vector V in V, remember that, right, bracket V B, right, is equal to, right, the vector x1, no, let's not use x, a1 to ac, such that, well, is the unique vector. Of r to the c, such that a1 v1 plus, oh, I'm using the letter v too many times, aren't I? We'll call these w's. Such that a1 w1 plus ACWC is equal to V, right? It's the linear combination for V given by W's, or the V as a linear combination of the W's, the B vectors. All right. Note also, right, that W1 with respect to basis B is just the elementary vector 1, 0, 0, 0, like that, right? W2, the coordinates of W2 with respect to B, right? That was called the coordinates of V with respect to B. The coordinates of W1 with respect to B's are that. The coordinates of W2 with respect to the B's are this, you know, etc., etc. Right? That is W1B dot 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 WCB is the elementary basis for V as a vector space in R to the C. Right? So we have the elementary basis. Therefore, V as a, well, subspace as a subspace of RC is actually all of RC, because the elementary basis, it spans the whole of RC, right? Very simply. All right, now if you take, so that's great, right? I mean, given a vector space V, right, we think of it as R to the C, where the vectors, given a vector space V and a basis B, when you look at the coordinates of the vectors in V, with respect to B, it becomes just RC. And that's what we were saying, that, really vector spaces are all just R to the n in disguise. And that's the disguise right there. That's a general description of the disguise. All right, well, one thing that comes out of this that's very nice is the following. Let C equal to U1 to UM be another basis for V. All right, let that be another basis for V. What is M compared to C? They must be the same. So if U1 with respect to B through UM with respect to B, well, sorry, not, yeah. Just consider these vectors. All right, therefore, since C is a basis for V, these vectors are a basis for RC, right? Which is V in disguise, or V is RC in disguise, or however you want to think of it. Well, if you're going to have a basis for RC, thus the matrix A, whose columns are these vectors here, U1B through UMB, must have column space spanning RC. But that's true if and only if what? That's true if and only if A has a pivot in every row. Well, that requires M, the number of columns here, the number of vectors, to be bigger than or equal to C. Otherwise, if it's less than C, you can't have a pivot in every row, because a pivot, and the pivots go down. The pivots do what? Each pivot takes up a row, right? So you have to have at least C rows in order for there to be a pivot in every row. Also, because it's a basis, the columns of A are linearly independent. Well, that's true if and only if A has a pivot in every column. Thus, M is less than or equal to C. Right? Every pivot takes up a column. But you've only got, every pivot takes up one row and one column. Therefore, you have to have, every pivot takes up a column. So you can't have more than, I think I've got these inequalities wrong. Also, the columns in A are linear, and this is true if and only if it has a pivot in every column. Okay, so A has a pivot in every row and in every column. Since a pivot takes up one row and one column, A must be a square matrix, right, in RC. Thus, M, which is the number of columns, is C. Did I use the letter C twice? I did. Shouldn't use this, it's a capital C. Let be another basis for V. What should we call it instead of C? Just capital U, be another basis for V. Therefore, these basis vectors, right, there's M of them. These basis vectors are also a basis for RC. But the number of such vectors is again C. Therefore, by this argument, we have the following results. 1. Every basis of a vector space V has the same number of vectors in it. Every basis of a vector space V has the same number of vectors in it. This number of vectors is called the dimension of V. We'll define that later. 2. We'll define it now. The dimension of a vector space V is the number of vectors in any basis. The dimension of a vector space V is the number of vectors in any basis. Now, this can be infinite. I mean, you might have a vector space in which the number of vectors for a basis must be infinite. That opens up a lot of other sort of complications that we don't really want to deal with in this course. So all of the vector spaces that we look at really have finite dimensions, bases of finite size. Okay, did I get that going again? Yeah. The dimension of a vector space V is the number of vectors in any basis. So another result we have is the following. If V is a vector space of dimension n, then 1. Any set any linearly independent vectors v1 to vn automatically span V and so form a basis. All right, a basis is a set of vectors that's linearly independent and spans the vector space. Now, if you know the dimension of the vector space ahead of time, it's n. Okay, once you have so many linearly independent vectors, once you have n linearly independent vectors, you know that they automatically have to span V. 2, any spanning set of vectors, little v1 to little vn, are automatically linearly independent. And therefore form a basis for V. Why is that the case? It follows from the same argument that we had. Right? Considering V isomorphic to Rn, okay, the vectors v1 to vn are linearly independent. So if the columns of A equal to v1 to vn are linearly independent, then there's a pivot in every column. But there's n columns, and we're talking about Rn. Therefore, there's a pivot in every row. Right? So the column space of A is Rn. It spans. So v1 to vn is a basis. Also, if the columns of A span V, then there's a pivot in every column, or in every row. There's a pivot in every row. But again, A is an n by n matrix in Rn. So there's a pivot in every row. Thus, there is a pivot in every column. So the number of vectors in A, so the columns of A are linearly independent. Right? Thus, v1 to vn is a basis. And that's it. So knowing the dimension, so there's two things you need for a basis: a set of vectors that's linearly independent and spanning. But if you know the dimension ahead of time, linear independence and the right number of vectors automatically gives you spanning. And spanning and the right number of vectors automatically gives you linear independence. So knowing the dimension is like a second piece of information that you need. Right? There's two things you need: spanning and linear independence, or spanning and dimension, or dimension and linear independence. Right? Two of those three things will automatically give you the third. All right. Example. So let A be an R by C matrix. The dimension, and suppose that A has P pivots. has P pivot columns. Right? The dimension of the null space of A is the number of non-pivot columns, is right the number of free variables. And the solutions to AX equal to 0. Right? This is the number of non-pivot columns. Right? The free variables correspond to the non-pivot columns. This is C minus P. The dimension of the column space of A, like we've been saying, is the number of pivot columns. P. Therefore, what I was saying in a previous lecture is the dimension of the column space of A plus the dimension of the row space of A is equal to, right, C minus P plus P, just the number of columns of A. Always. Okay? So for any matrix A, right, that's just really one cool thing about row space and column space. Right? Their dimensions just add up to the number of columns, because one is P, the other is C minus P. Pretty neat. Okay? Alright, so that is the lecture for this section.